Today we'll try to discuss few more stuffs on capacitance, and then we'll do some experiments. And hopefully that will pretty much conclude whatever we want to learn in electrostatics. And the next part will be magnetostatics and few more stuff. So as you say, capacitance is defined as the ratio between charge and voltage. C is equal to and in case of parallel plate capacitor, we can write capacitance as EA over D for parallel plate capacitance. And for a sphere, the formula for capacitance is 4 by epsilon r, where I use the formula Q over D. D for the sphere is Q over 4 by epsilon r. So if you simplify it, you will get the final result. So these are two special expressions for capacitance. This is for parallel plate capacitance, and this is for a sphere. And this is the general equation for capacitance, Q over D. So, if I have let's say we have a sphere which has a radius of maybe 3 centimeters. For such a sphere, what will be the value of capacitance? So we know that capacitance is, for a sphere, is 4 pi epsilon r. So 4 pi epsilon r would be the value of the capacitance. If you plug in the value of radius 3 centimeters, what will you get? So 4 pi multiplied by epsilon is 10.85 into 10 inverse 12 farad per meter, multiplied by the radius r, which is 3 centimeters. That means 3 multiplied by 10 inverse 2 meter. If you plug in all the numbers, what do you get? Alright, so instead of using calculator, a simple way to use your justification is the following. 4 pi is almost 10, like 12, right? So you are multiplying this guy. You can take this guy as just 10. So that will simplify stuff a lot. So this is 10, this is another 10. So we have 10 cubed here, and we have 10 inverse 2 here, and then we have 10 inverse 12 here. So we should get pretty much around 10 inverse 12 and 10 inverse 11, something like that. And we get whatever we get from the calculator is the exact answer. My point is that even without going to calculator, you can just look at the power of 10 and get a ballpark. So it's actually, should I do this fans? Pardon?
Should that C in the unit speed?
Oh, I'm so sorry. I'm so sorry. Thank you. It's bad. Thank you so much for catching it. So it's actually 3.34 picofarad. All right. So the question is, if I apply a voltage, let's say I have a battery and I touch one positive terminal of the battery to a sphere. If I do that, then I should induce some positive charge on the sphere. And let us say that the negative terminal is at the ground. So the question is, if I apply, let's say, a 5-volt battery and touch on the sphere, how much charge am I going to induce on that sphere? Is it possible to find it out based on whatever we learned here? How can I do it?
WC times V.
So I want to find out the value of Q that is going to be induced on the sphere, given we have 5-volt battery touch on it. So we know the value of C, and we know the relation between C, voltage, and charge Q. So based on that, we can say that Q is actually C multiplied by V, right? So we just figured out that the capacitance of a sphere, which is 3 centimeters radius, has a picofarad capacitance. So I will just say 3 picofarad capacitance, and then you multiply with the voltage. So, and then you will get your result, which is what?
times 10 to the negative 11.
It's a very small charge, right? Picofarad charge. So did you notice that in order to hold more charge on the sphere, I need to go to a bigger sphere, right? If I go to a bigger sphere, my C would go up, and then the corresponding charge would also go up, right? So if I take 2 spheres, let's say I take another sphere, which is smaller than the previous sphere, and I make connections between them. So now I have a configuration where we have 5-volt battery. The positive terminal of the 5-volt battery touches a bigger sphere, and then other terminal is grounded. The bigger sphere is also connected to a smaller sphere. So I expect that both of the spheres will have same type of charge, right? So this guy would also have some positive charge, right? Now which guy would have larger amount of charges between these two guys? Which one will have larger charges? Bigger charges. Speak out loud.
A larger sphere.
Larger sphere. Does everyone follow? The bigger guy will have more amount of charges because this guy has more capacity. Which of these guys will have larger voltage? The smaller guy or the bigger guy? So you say that the charge will be higher for the larger guys. And the question is that which one will have larger voltage? Okay. let me draw a mechanical stuff. So let's say I have two pots. One pot looks like this, and the other pot looks like this. All right? And both of these pots is filled up with liquid. And then I connect both of these pots by a pipe. Now the question is, at the equilibrium condition, what would be the level of those liquids? Where they would reach an equilibrium? Will the bigger pot will have a higher height of the liquid, or the lower pot? Or they will be same?
The same.
Everyone agrees that it should be same? Right? It should be same. If you take a course on mechanics, it should be pretty obvious to you that if we take a pot which has a larger height of liquid and connect it with a smaller pot, then the liquid will start to flow from this guy to the other guy until both of them reaches the same height. Okay? And how do you know what is the pressure of liquid on both of these pots? You can use the formula of mgh, where m is the mass of this liquid, g is the gravity, and h is the height. So both of these guys will reach equilibrium when when h is same for both of them. Okay? And in a similar way, if you take two spheres and connect them each other, then there will flow charges between them until the voltage becomes equal. So look at the previous condition where we have the mechanical diagrams, and the liquid, they start to flow from one guy to another guy until their pressure becomes equal. Remember, the pressure does not depend on what is the value of weight of the liquid. The pressure only depends on what is the height of the liquid, right? But it's possible that at the height, when they will reach equilibrium, maybe this is the condition where both of them will have the same height, so same pressure of liquid. But it's quite possible that this guy will still contain a lot of liquid compared to the other guy. So I can make it very narrow. I can make it really, really narrow. To make it obvious that the smaller guy contains a less amount of liquid compared to the other guy. So the amount of liquid can be very high, but the pressure of the liquid will be same for both of these pots. In the same way, the amount of charge will be very different between these two guys, but the voltage must be same at equilibrium for both of the spheres. Do you follow? So back to the question. If I apply 5 volt voltage on the bigger sphere and connect the smaller sphere with the bigger sphere with this conducting wire, how much voltage do I expect at the smaller sphere? Same voltage, right? So this is also 5 volt, and this is also 5 volt. Okay. Remember that the time, let's say that you made a switch between them, so you can connect or disconnect between bigger and smaller sphere. The moment the switch was off, the switch was open, the smaller guy didn't have any charges. So this means it has 0 volt. But by the time you turn on the switch, all the charge will start to flow to the other guy as long as the smaller guy reaches a voltage of 5 volt. And at the time both of these guys have 5 volt voltage, there will be no more charges, so there will be no more current between the wires. So that's called the equilibrium condition. All right. So let us see if we can measure it. So what we have here is like more or less a sphere. Of course, it's not a perfect sphere, but I think if we still use the equations of 4 pi epsilon r, we may get a ballpark idea of what is the capacitance of this guy. Remember that we are not trying to get into the details of 3.34. It's not possible, first of all, because we don't know what is the value of r, and also it is not a good sphere. But we expect that the capacitance for this guy would be in the range of picofarad. So you can get a ballpark idea. So let us see if we can measure it. So on my hand, I have an LCR meter. I'm not sure if you have heard about LCR meter previously. So LCR meter stands for inductance, capacitance, and resistance measurement. So I'm not sure if I can throw it on the screen. Last time it didn't work. So this time again I will borrow somebody. Not Isaac, because Isaac got some privileges on the other time. So maybe somebody else who is going to help me. So your job is very simple. Just you will read it out, the reading from this multimeter, and tell it to your friends. Before I start, I want to tell you that even if I do not touch anything, let's say I have some readings. You can see probably, right? You don't need to see what is there, but there is some reading. It's not zero. So we are measuring capacitance, and we are seeing some value which is not zero. That means these values are actually background noises. So we are going to just ignore these background noises and try to add on top of it. So let's say I'll show it to somebody. Okay? Maybe I'll show it to somebody in the middle. Okay, I don't need to touch actually, right? So maybe I should go this way. No, you guys, no, too much. How about this? So you see that this is a background noise. Yes. So if I touch the capacitance, we expect that the background noise, on top of the background noise, we should have some real value. And we expect that this value would go up to picofarad range. Maybe I indeed need somebody to just come over. Any volunteers? No?
Sure, I'll do it.
Thank you. So, Kevin, if you can come this way. So, I hope you trust him. And you can see what are the background values, right?
Yeah.
Around 20.
Yeah, 24.
Okay, it's moving too much. So let's get it to settle it a little bit, and then we'll touch. So it's something like 20, right?
Mm-hmm.
And you're measuring capacitance?
Yes, we are measuring capacitance. So remember that in order to measure capacitance, we need to apply some voltage, and we have to measure the charge, right? Now, this guy, the meter, LCR meter, it has a battery inside it. So what it does is the following, that whenever I apply the probe, whenever I touch the probe on this capacitor, then it tries to apply the voltage on this guy, and then try to measure the current. So if you can measure the current, if you can also measure how much time it takes to flow the current, you can multiply current with time to get the value of charges. So once you get the value of charge, you can divide it by voltage and to get the capacitance. So I'm going to touch this guy. So right now it's around 20, right? Mm-hmm. 20, and look at the corresponding unit.
Yeah,
So PF stands for picofarad. So the background noise is already 20 picofarad. I'm expecting that it will go a little bit up, maybe some more picofarad, but not beyond that. So if I just touch it,
It did increase, but just a little bit.
just a little bit. And it doesn't need to be, I mean, we know that it's not going to increase too much because it's 3 picofarad, right? Sure. Not more than that.
Right. It was about that much.
Right. So the background was 20 picofarad. When I touched it, it went up to 25 picofarad, which is not bad actually. This is what we expected. It will be 3.3 picofarad, right? Now, if I, Gavin, if you can hand over that guy, smaller.
Okay.
So,
What'd you touch?
you blew it up. All right. So, if I try to measure the capacitance of this smaller sphere, what value do you expect?
Small.
Yeah, small, but let's be specific. What value do you expect? You know the value of this guy is 3 picofarad, something around 3 or 5 picofarad. So what value do you expect here?
1.2 picofarad.
Yeah, very good. So now you know how to be specific, not only just small. It could be picofarad for sure, right? But maybe just maybe half of it, but not more than that. So previously I think we measured it to be 5 picofarad. So if I try to replace it with a smaller sphere, what is the background here? The background will keep changing. So maybe we have to just eye gaze it. So it's like 22.
Yeah.
That's what's here. Okay. So if I 22.
Yeah. What if I like half?
Yeah.
Yeah.
So something like 1 picofarad, 1.5 picofarad, not more than that, right? So that matches with your expectation that it is in the picofarad range, but it is not 5 picofarad, it's a little bit less than that. So based on those two results, you can actually guess that how big are those spheres are. So if you know the sphere size for one guy, you can actually back calculate what is the size of the other sphere. Like it should be at the same ballpark, but maybe half of it. Okay? So you can use this idea to actually measure the size of devices, of stuff. I mean, for these guys, it's actually easy to take a scale and measure it. But if your device is very small, then you can use the other idea. What if you measure the capacitance? Let's say that your sphere size is 1 micron, and this other guy has a sphere size of 0.5 micron. You cannot use a ruler, right? But you can use a capacitor. You can measure the capacitance, and based on your idea, based on your reading, you can reverse what is the size of those devices. Do you follow what I'm saying? So it's not that you always are given a particular size. Maybe this size is unknown to you, but you can measure the capacitance and go back to what is the corresponding area, or what is the size of the device. Okay? All right, Gavin, a few more minutes and then I'll get it. Okay. So, so what I have here is a Wimshurst machine. I hope you guys already know it. We discussed about it some time back. But if you forget, here is again a quick brief. This machine is supposed to create charges on both of those two spheres. If I apply some mechanical rotations on the back, then because of the friction, it deposits charges, and those charges will be accumulated on the positive and negative sphere. Okay. So, and you know that if I keep rotating this disk, at one point of time, there will be so much charges that it will break down, and the air will see a breakdown, a discharge through positive and negative sphere, right? So let's try repeating that idea one more time. And once it gets enough charges, I will ask Gavin to put his hand in between so that he can get that. So let's see. Okay. So it works. Now the question is, previously we just knew that if we keep it rotating. At one point of time, the voltage will be so high that the medium, the air medium between them, they will break down. So the air itself is an insulator, but if we create enough voltage, then the insulator will break down and insulator will behave like conductor to carry charges. Now the question is that, can you also find out at what voltage this guy is going to break down? Now we are even more mature, so maybe we can quantify. So our situation is the following. We have two spheres. And those two spheres have positive and negative charge. And in between those two spheres, we have air. Air is an insulator, but if you keep increasing the positive and negative charge, the voltage of these two spheres will increase, and on one point of time, it will discharge to the air. Now, if we try to understand at what voltage does this discharge occur, we need to know what are the breakdown voltages of the air. So breakdown voltage of air is, can anybody help me to find out the breakdown voltage of air? Just Google it.
Okay.
Go ahead.
30 kilovolts per centimeter.
30 kilovolt
Per centimeter.
So 30 kilovolt per centimeter. Right. Okay. So, based on what you see here, you know that at one point of time the air is going to break down. Can you tell me, when this guy will break down, what will be the voltage between the positive and negative PI? You just figured out that 30 kilovolt per centimeter is needed in order to break down the air. Now tell me, what voltage should be there in order to reach that 30 kilovolt per centimeter?
150 kilovolts.
Yeah, I would say something like that, yeah, like 200, something like that. Because we just need to know how far apart these guys are. So I would say these are like 4 centimeters. So I will just multiply 30 with 4 to get like 120 kilovolts. So it's a lot actually. Can you believe that this guy has 120 kilovolts?
No.
No, right? No way. Impossible.
If friction can create that much voltage, that's ridiculous.
So how do you say that I don't believe it? It cannot be 30 kilovolt, or it cannot be 120 kilovolt. What? Please go ahead.
I just don't think the friction between the metal and the little things on the machine can create that much voltage.
Okay. Can you tell me more? Like, you say that it cannot create that much voltage. Do you have any other reference on which you can make a comparison?
Well, friction in the thermal sense, something that is bigger creates more friction than the heat is bigger.
That's true, but when I say...
So based on size, then electrically the same principle, something smaller cannot create that much friction to create that much voltage.
I'm saying that you said it's not possible. So do you have a reference on which you can make it? For instance, let me give you an example what I really mean. Let's say I tell you that I saw a man who is 10 feet long, like who is 10 feet high. You don't believe it, right? Because you know all people, and they pretty much average 5 to 6 feet, not more than that. So 10 feet is pretty much an unusual value, right? So you know that 10 feet is an unusual value because you have some reference in mind. In a similar way, when I said it creates 120 kilovolt between these two balls, do you have a reference on which you can make a measurement and compare?
Our outlets are like 100 times less, 1,000 times less than that. So.
Right, right. So the outlets that you see here, it is 110 volt, right? If the outlet, and you're sure that if you plug in your finger there, of course you'll be dead. So for sure, it has a very high voltage. Now I'm claiming that this guy has 1,000 times higher voltage compared to what you see in the outlet. That should ring a bell that something is not right. It doesn't make any sense, right? I guess that was the idea, that why you canceled out the previous thought that it can have 120 or 110 kilovolt voltage. Okay, let's go back. Let us take these examples. Remember that voltage corresponds to the pressure of liquid, and charge corresponds to the amount of liquid. So charge, in other words, charge corresponds to M, and voltage corresponds to H in mechanical sense. Okay? So, is it possible that one guy would have a very high pressure but have a very low charge? Think about it. I want to say a situation where the beaker will have very high pressure of liquid but very low amount of liquid. Is it possible? Can I make a beaker which satisfies this condition?
Yep.
I want H to be very, very high, but I want M to be very, very low. And if I want to satisfy this condition, how should I make the beaker?
Small.
Tall and skinny.
Tall and skinny, exactly. Make a beaker like this. It will have a huge pressure, right? But the amount of liquid is very small, very, very small. I can make it arbitrarily small. Now think back in the domain of electromagnetics. I said that the pressure of liquid corresponds to the voltage, and the amount of liquid, M, corresponds to the charge. So is it possible to make a case where I will have very little amount of charge but very high voltage? It is possible. How it is possible? Let's look at here. So I have a battery, and I say that if I attach the battery with a sphere, let's say this sphere is 3 centimeter radius, and it has a battery of 5 volt, okay? And then it will create some charges, right? Now, I can do the following. I can make this guy very small, right? If I make this guy very small, let's say instead of 3 meter, if I make it 3 micrometer, really, really small. Will I have same amount of charge if I make it small, from 3 centimeter to 3 micrometer, or different? Always remember that Q is CD, and C is actually 4 pi epsilon r multiplied by. So if you reduce the value of radius, then C is going to reduce, right? Then Q is of course going to reduce. How about V? Will the voltage reduce if I take this 3 centimeter guy and somehow squeeze down to 3 micrometers? Will the voltage reduce? The voltage will remain the same because it's 5 volt battery, right? But the charge reduces. Charge will drastically reduce by probably 100,000 times, probably 1,000 times, or even more actually. So it is possible to have a very high voltage, really, really high voltage, but have a very low charge. Okay? It's the same thing what you see in mechanically. That we can take a beaker, make it really tall and skinny, so that it can have a very high pressure of air. But is it a killer? Like if I put you under it, will you die? No. Do you understand, right? It has a very high pressure. And I put Kevin here. And I believe he will be still smiling. In fact, we have this huge pressure, the atmospheric pressure of the air. We have a big pillar of air, right? And we're totally comfortable with it. It's not a problem. So the big pressure will not create a trouble because the amount of charge, amount of liquid is very small here, right? If I make this guy, let's say, not skinny, maybe very thick and fat, will I change the pressure? No, I won't. I will not change the pressure. The pressure is same. Pressure always depends on what is the height of the liquid. So height doesn't change, pressure doesn't change, but will gas survive? No, because look at the M. The mass of the liquid is very high now, right? Because now it is very wide and thick. So you understand that pressure itself cannot kill you. In a similar way, the voltage itself cannot kill you unless the charge is very high.
So in the skinny and the fat, are you putting the same amount of liquid in both, or are you?
No, it's not possible, right?
They're just both full, right?
They're both full. They have the same height, they're both full, but for the skinny guy, we have a very less amount of charge, a very less amount of liquid. Okay? So the pressure, mechanical pressure that you get from the skinny beaker is very high, but because the amount of liquid is very small, so we won't have any problem to bear it. But if we have a very thick guy, full to the brim, we'll have the same pressure, but this time we'll have a lot of pressure. I mean, we'll have a lot of problems to bear it. In a similar way, in the electromagnetic case, we can have very high voltage, but very low amount of charge. So it may not be a problem for us to deal with a very high voltage, given the charge is very small. So in the case of this guy, you can see in your eyes that the air is breaking down, and Google says that the corresponding breakdown voltage is 30 kilovolt per centimeter. That means the voltage between this guy and this guy is actually 120 kilovolt, which is 1,000 times larger than your inlet, power inlet. But it's not a problem for you. Like, you will get a shock a little bit, but it's not too much because the amount of charge is very less. On the other hand, the power inlet, it has a voltage of 110 volt, but it has a charge which is very high. Okay? Very, very high. In fact, it has an infinite amount of charges. It can keep flowing the charges as long as you want. That's why it's problematic. We cannot sustain that. Okay. Now do you understand that high voltage does not always mean it's a bad thing. Of course, high voltage transmission line would be disastrous for you because those transmission lines can carry a lot of charges. They can continuously supply charges. This guy is a very low amount of charges, and that's why even if it has a very high voltage, it's not a problem for you.
So you can put your finger in between that and it won't hurt you.
Yep. I'll just feel a little tingling, but that's all. Any question? Oh, you want to try it? You can try it. Yeah, yeah. I mean, thank you. Thank you for volunteering.
Man, you got Isam, you got an interview to think about. What are you doing?
Oh, yeah.
So this time I'm a little nervous, but I appreciate that you try this out.
Wait, are you sure?
Yeah.
Okay.
Okay, how about this? Just to reduce the feeling, what if you do not touch it directly, but let's wait for some time and I'll tell you. Okay?
All right.
So maybe I will not crank it up to the highest level. Okay, just start it. Just start it.
Look at that.
Thank you so much. I really appreciate it. I really appreciate it. So, you really proved that what you understood is what you believed, which is really important. Like, not many people will see stuff, will do the stuff in math, but they will not risk their life believing it. But it is true, you can really sustain kilovolt amount of voltage. Why? Because the charge is very small. Isn't it fascinating? Alright, so one more thing before we finish it up. I say that the amount of charge depends on how large the object is. You can have same voltage, but if you make this guy very big, then the amount of charge will also go very big, right? Likewise, if you make it small, if you make your sphere small, then the corresponding charge is also going to be small, having the same voltage. So you can also see that this entire device has some spheres, has two spheres. It also has some jars, right? So maybe I have not talked about the jars previously. But what does this jar do? I forgot the name of the jar. Anyway, so these jars are basically some capacitor. Okay, it has a specific name. I forgot what is the name, but it's a kind of capacitor. Okay, it can also hold charges. All right. So you know that if I have a sphere, how to calculate the corresponding capacitance by using this formula, 4 by epsilon r. But in case we have a jar like this, Leyden jar, right? Thank you so much. It's called Leyden jar. Now, this jar also can contain some charges. So, there is a knob, like a switch, that can be used to either disconnect or connect with the jar and the sphere. So, if you look it sideways, you'll know that this sphere is connected to the metal, and this metal, we can put another switch so that this metal is going to connect into the jar here, okay, through this switch. So the question to you guys, let me show you one more time here. So we have a switch. If I turn off the switch, then these spheres will be on their own. But if I turn on the switch, then these guys is going to be touched. It's going to be metallically connected with the jars. Okay. So the question is, if I disconnect those metallic spheres from the jars, will I increase the capacitance or decrease the capacitance?
Decrease.
I'll draw it here. So we have two cases. In one case, the sphere touches a Leyden jar. The jar can contain charges. The sphere also can contain charges. The question is, if I can somehow disconnect between the jar and the sphere, will I increase the capacitance of this guy or decrease? Decrease. Everyone follows? Of course, I have not defined what is the capacitance of the jar, but you understand that the bigger a guy becomes, the bigger an object becomes, the bigger its capacitance will become. Okay? So capacitance is directly related to its size. So if I reduce, if I can disconnect this sphere with the Leyden jar, then the capacitance of this sphere will be reduced, right? Okay. Now tell me this. If I disconnect both of this guy, so that now the jars have no role in making a charge, because these jars are just mechanically, these jars are metallically disconnected from the sphere. If I keep rotating the sphere, what will happen? What is your guess?
It'll take longer to discharge because there's
It will
less
take
charge.
longer to discharge? Why?
Because there'd be less charge, so it takes longer for, or sorry, there's less area for charge to build up, so it takes longer for it to build.
Okay. So when you find out the breakdown voltage of air, you say that the breakdown voltage is 30 kilovolt per centimeter, right?
Yeah.
So in order to reach a voltage which is 30 kilovolt, let's say we have two spheres. One is small and one is big. And you are flowing the same amount of current let's say we are flowing 1 milliampere current and also 1 milliampere current to both smaller sphere and bigger sphere, right? Which guy would let us say that the smaller sphere is connected to a battery, the bigger sphere is also connected to a battery. Okay? Now the battery has a switch. Does everyone understand what is drawn here? We draw two different spheres, one small and one big. Both of the sphere has a battery associated with it. The battery rating is same, let's say it's 5 volts, this is also 5 volts. And I'm going to connect those batteries with the spheres. The moment I connect, the battery will charge the spheres, right? Which guy would reach 5 volt voltage faster? Smaller. Why? Why the smaller guy would reach 5 volt faster? Let's charge. Let's try to understand. If I turn on the switch, then both 5 volt voltage will try to charge the smaller guy and the bigger guy. But the smaller guy would need less amount of charge to get to the same amount of voltage. Right? Always remember that Q is CV. So the smaller guy has a lower capacitance. That means in order to get the smaller guy to the same amount of voltage, we need less amount of charge. On the other hand, the bigger guy will need a large amount of charge to get to the same voltage point. Right? So now come back to this situation. We say that we previously those large sphere, they were connected to the Leyden jar, and now we disconnected them. So of course we reduce the capacitance between them. So the question is that if I rotate the disk, what's going to happen?
Opposite of what I said. So discharge faster.
It will discharge faster. Do you understand that why it will discharge faster? Because it will reach the same breakdown voltage of air by shortest amount of time. Previously, when they were connected to the Leyden jar, it would take them a long time to reach the 30 kilovolt per centimeter voltage. Now it will reach faster, right? And it will have less amount of charge, right? So if it has less amount of charge, we should see less amount of discharge also through the air. Previously, the spark that you see, the discharge that you see, that were very bright. But if I disconnect them, then it will reach the same amount of voltage with less amount of charge. That means now the brightness of the spark would be reduced, right? So let us see. Hang on a second. So, okay. So I disconnected, and I'll try one more time. You see this? Do you see the spark?
No.
There is no spark. Why there is no spark?
It's too fast for us to see.
Of course, it's too fast, and look at the amount of charge. Now the capacitance is reduced. So the amount of charge to get to the same voltage is also reduced. That's why the discharge that you see is almost invisible. But it reaches the same voltage. Because without having 30 kilovolt per centimeter, you cannot break through the air. You can still hear this noise, right? The noise actually coming from the breakdown of the air. But you cannot see that it's as bright as you saw it previously. Because the amount of charge is very small. Because I reduce the capacitance. Do you follow what I'm getting here? Alright, so you understand that a simple formula like C equal to Q by V could not be very straightforward to understand. Like it could be really counterintuitive at some point of time. In fact, the way we build up our understanding on how voltage works or how current works, it could be quite confusing at times. Right? So you understand today that high voltage does not always mean it is killing. High voltage could be totally safe as long as the corresponding charge is very small. In power outlet, we have 110 volt, which is very dangerous for us because it has a lot of charges. Here I have 120 kilovolt amount of voltage, But it's totally safe because the amount of charge is very small. Okay? And how to know whether the charge is very high or very small? Just look at the capacitance. If the capacitance is very high, most likely it is going to contain a lot of charges, and that's dangerous for you. If the capacitance is low, it could have very high voltage, it could still be safe for you. Do you follow? All right, so I think, yeah, we spoke a lot today. Next week we are going to start a new topic, electrostatics, and we'll go from there. Thank you guys. Thank you for your attention. And thank you so much for risking your life. Have you, by the way, have you, by any chance, seen the videos of Walter Lewin of MIT? So he's a professor of physics. Have you heard of him?
Yeah.
No. Okay. So Walter Lewin is a famous person who actually not only teaches the class, but he also demonstrates every time with new experiments in the class. So in one of the class, he tried to do the following. I'll show you just 1 minute before I release you guys. So let's say we have a simple pendulum where we attach a big ball with a string, and we disturb it from the equilibrium. We take it a little bit sideways and release it. Then we all know that what's going to happen. This guy is going to oscillate back and forth, right? Back and forth like this. But it will never going to cross beyond its previous amplitude. Let's say you displace this guy from the equilibrium by an amplitude of A. Then of course, its rotation is going to be limited between plus A and minus A. And this is the equilibrium point. So around the equilibrium point, the maximum displacement of this sphere would be plus A and minus A, right? Everyone understands it. And nobody will argue on it. Now he did the following. He said that this plus A and minus A, it actually comes from the energy conservation principle. Because of the energy conservation, it can never go beyond minus A or beyond plus A. Now he did the following. He took a very, very big sphere and very heavy sphere and attached it with a very big string, hung it from the roof of the class. And so this is the class. The entire classroom. And the professor himself, he stood here. And he took this ball the ball is very heavy. He took this ball and touched that ball to his chin. Okay? Exactly on his chin. And then he released it. So if he releases the ball is going to travel all the way up there and it's going to come back. He stays still. He says that if I know that this plus A and minus A is always going to be retained, this ball will never cross plus A. That means that if he touches from the, he releases the ball from his chin, the ball will come back and just touch his chin, but it will not crash him. Right? So he did that. Everyone actually, they were scared. I knew that people were scared, but the professor knew that the physics actually works, and indeed it works. So it didn't kill him. It really stopped right at the position of the chin. So the point that I'm trying to drive in is that doing something on a piece of paper and actually believing something in your life is not actually same. They could be very different. So I really appreciate that you took your life risk and really believe that despite it has a very high voltage, it may not have very high charge, and that's why it could be safe. I really appreciate it. You really just remind me what Walter Lewin did some time back. And it became a very famous video. If you just search with his name, I'll write his name actually. Walter Lewin. I think think he retired already, but he's an emeritus professor, and he still inspires many other people like me throughout his excellent work. So thank you guys. I hope that you enjoy the class, and we'll meet you.